Thank you very much to Professor Jesus da Pena to be with us this evening. We are looking forward to hear him talking about high jump. So let's start. And Professor, it's up to you.
Okay, very good. Well, thank you very much. I'm very happy to be here. My name is Jesus da Pena. I'm a specialist in biomechanics. I am originally from Spain, but all my professional life has been in the United States. I was a professor at Indiana University, but between 1982 and 2007, for 25 years, I was the biomechanist in charge of the high jump event for USA track and field, which is, as you know, is the American equivalent of FIDAL. So every summer, my students and I would go to the main competition of the year. Normally, that would be the National American Championship. In an Olympic year, it would be the Olympic trials, which is that year, that's more important than the National Championship. So we would go to this competition and we'd film every jump of the men and women high jumping. We filmed it with 2 cameras. Then we go back to Indiana, and here we would measure in the films, we'd take measurements, and we would be able to reconstruct in 3D, 3 dimensions, how the athletes moved during their jumps. So at the end of that, I would write a report, and this written report would go to the athletes from the competition and also to their coaches. And I would explain what the athletes were doing in their jump for their technique, and what they were doing right in their technique and what they were doing wrong in their technique, and some advice on what changes to make. So then around that happened in the summer and in the fall. And then around January, I would meet with the coaches. I would go from Indiana to maybe Colorado Springs or San Diego, someplace like that. So I would meet with the athletes and their coaches, and I would clarify any questions that they still had. And then the coaches used this information during the winter as they prepared for the following season. And in this January meeting, I would always give a lecture on the biomechanics of high jumping technique. So I explained how the high jump works mechanically, and also I would explain why moving in certain ways would help to improve your results. And this Zoom presentation, this is part 1. This Zoom presentation will contain essentially the same information as those lectures that I used to give to the athletes for USA track and field. Okay, so let's get started. Here we go. Let's see, share screen. Okay. And here we go. So can everybody see that first slide?
Yep.
Yeah. Okay, the biomechanics of high jumping. Oh, one thing I have to do, wait a minute. I have to get my pen ready here. Pen. And yep, that works. Okay, so let's go to the next slide. Okay, when we look at a high jump, we can break it down into 3 phases. There's a run-up phase, a takeoff phase, and an airborne or bar clearance phase. Of these 3 phases, the takeoff is the most important one. It's very short. It's the shortest of the 3. It lasts somewhere between, very roughly between 0.16 and 0.18 seconds, something like that. That is the most important part of the jump. Now, the run-up, so that's the takeoff, most important part of the jump. The run-up in itself is not important, but the run-up prepares the conditions for the beginning of the takeoff phase, prepares the conditions for this instant here, which is the start of the takeoff phase. And because of that, the run-up also becomes very important. Now, the third phase, the bar clearance, that is the least important part of the jump. I mean, is the spectacular part, the part that the television cameras show that everybody loves, but most of what happens in the bar clearance, not everything, but most of what happens in the air is determined by what happened in the run-up and the takeoff. So the bar clearance is the least important of all the three phases. So as I explained the technique, it would seem logical that I would start by explaining how the run-up works, then how the takeoff works, and then how the bar clearance works. However, we're not going to do it that way. I'm going to look first at the takeoff phase, because when we look at the takeoff phase, we will be able to understand what you need to do during the takeoff, and therefore we can say what you need to do previously during the run-up in order to prepare for that takeoff. So I'll be talking about the takeoff, and that will tell us things that we have to do in the run-up. And the bar clearance, we probably will not deal much with it today. That'll be a later lecture. Okay, so these two pictures show the beginning and the end of the takeoff phase. And first we're going to be looking at what happens in the horizontal direction during the takeoff phase. So at the end of the run-up, or at the start of the takeoff phase, in the same instant, the athlete will have a large horizontal velocity, not as much as a long jumper, but it will be a good horizontal velocity. Maybe it's this velocity here, and that's maybe about 7 or 8 meters per second. So for a Olympic level, good Olympic level male athlete, it will be about 8 meters per second. For a good female Olympic level, it would be about 7 meters per second. So the athlete comes in fairly fast. Then the athlete plants the foot on the ground and pushes forward on the ground. Then the ground, by reaction, pushes backward with this force that you see here. So that force points backward and slows down the athlete. So by the time the athlete leaves the ground, the speed is this value here, which is smaller. So maybe this value here, I don't know, can you see my pen moving?
Yep.
Yeah, okay. So this velocity here of maybe 7 or 8 meters per second, by the end of the takeoff phase, it turns into about maybe 4 meters per second. Okay? Now, if we think about a long jump instead of a high jump, you don't want to lose horizontal velocity in a long jump. You will lose some, but you try not to lose it. In the high jump, it's different. In the high jump, it's normal, and actually it's good to lose horizontal velocity during the takeoff phase. What is the purpose of having these velocities? Well, this final velocity, this one here, that is necessary because if you had no horizontal velocity, you would go straight up and come straight down. You would go like this, up, and then down again in the same place. And that's not good. The officials want you to make it to the other side of the bar. So because of that, you need to have some leftover horizontal velocity. That's not very difficult to do. It's very easy to have 4 meters of horizontal velocity. But this horizontal velocity here at the start of the takeoff phase, we're going to find out later that that is very important. Okay, so that's what happens in the horizontal direction. You arrive at the takeoff phase with a large horizontal velocity. You make a forward force on the ground. You receive a backward force from the ground, and your horizontal velocity gets reduced from 8 to maybe 4 meters per second. Now we'll look at what happens in the vertical direction. Okay, in the vertical direction, initially, when you put your foot on the ground, you have a slight downward vertical velocity, this small downward arrow you see here. Maybe it's minus 0.2, minus 0.4 meters per second. And that's very normal. This is like any time, let's say you're a sprinter running, in every step of sprinting, when you're leaving the ground, you have a slight upward vertical velocity. And with that very small upward vertical velocity, you reach your center of mass of your body follows a parabola. It follows a path that you go a little bit higher than a takeoff point. You reach a peak and then you come down. And when you put your foot on the ground to start the next step, you have a downward vertical velocity. In the same way, a high jumper at the end of this last step of the run-up, he or she will have a small downward vertical velocity, maybe minus 0.2, minus 0.5, something like that, meters per second. I mentioned before, I talked about the center of mass. And I think I should make a little apart here to talk just a little bit about the center of mass. The center of mass is a point that defines the average position of all the parts of the body. So it's not attached to any particular organ of your body. It's just an average of all body parts. And here I'm marking it with a red dot. Okay, we'll talk more about the center of mass later on. It's also called the center of gravity, is the same thing. Okay, so we're here at the start of the takeoff phase, and we have a small downward vertical velocity. Then during the takeoff phase, I said before that you push forward on the ground, but you also push downward on the ground. And by reaction, the ground pushes upward with a very large vertical force that is much bigger than your own body weight. And that upward force changes your vertical velocity from a small downward value here to a big upward value at the end of the takeoff phase. Maybe for an Olympic level athlete, maybe 4.4, 4.7 meters per second of upward vertical velocity. So that vertical velocity at the end of the takeoff phase is very important. It's the most important thing in the high jump. If you ask me, what do I want from Sotomayor for my jump? I want this vertical velocity at the end of the takeoff phase. That's what I would want. Because that vertical velocity, let me put here, this is the center of mass at the end of the takeoff. And that upward vertical velocity determines how much higher your center of mass goes from the takeoff level, which is this level, all the way to the peak of the jump. It determines this distance here that I'm drawing. Okay? So what we want to do is we want our vertical velocity to change from a small downward value at the start of the takeoff phase, minus 0.2, minus 0.4 meters per second, to the biggest possible upward vertical velocity at the end of the takeoff phase. So how do we produce a change in vertical velocity? Well, there's two ingredients that you need. To change your vertical velocity, you need to receive from the ground a large vertical force. The bigger, the better. And also, you need to receive that force over a relatively long time. The longer, the better. Now, that time is never going to be very long. Remember, the takeoff phase lasts somewhere between 0.16, 0.18 seconds. So a short time would be 0.13, 0.14, and a long time would be 0.20, maybe. Okay, so it's going to be a short time available for getting this vertical force, but you want it to be relatively long. Okay, so you need a large vertical force over a long time. And we're going to look first at how can you make that vertical force be very large. All right, so to try to understand how to obtain a large vertical force, we need to talk about muscle mechanics. Muscles have very special properties, and we want to exploit these properties as well as we can. Okay, so we're going to move away from the high jump for a little bit, and we're going to be talking about something else. We're going to invent a new track and field event. It's going to be, it looks like a shot put, but it's not really a shot put. There's a person sitting on a chair maybe, and you have a shot in your hand, and a peso, and you have to throw it. It's not a real shot put. It's just you have to extend your arms and throw this shot with the biggest possible velocity. You push it as hard as you can, trying to see how far it will go. So for that, the muscle that we will be using will be the triceps, which is this muscle here. Okay, so now, so you've thrown the shot, you've made a big effort, and it goes whatever number of meters away. So then they say, okay, now let's change this. Instead of throwing the shot, we're going to be throwing an apple. So an apple has much less mass than a shot. If you push on it, it moves very easily, very quickly, gets a lot of velocity. So the apple is going to travel farther away, is going to land farther away. The apple is going to move more quickly than the shot. And at the time that the apple leaves your hand, it's going to have a larger velocity. Okay? It's a very fast motion. Now, after you throw the apple, you find that, yes, it went farther away than the shot. And then I'll ask you, how did it feel? How did your muscle feel? Did you feel that you made as much force as when you threw the shot? And you'll say, well, not really. It didn't feel that way. It felt that the apple yielded too easily. It just got going too soon. And I did not have an opportunity to really push hard on the apple. My muscle didn't seem to make much force. And if we measured your force, there's ways to measure it. Indeed, you would be right. The force that you're making with your muscle will be smaller when you're throwing the apple than when you're throwing the shot. So you have activated the muscle, your nervous system said to the triceps, okay, activate really hard, try to shorten very hard. And in the first case, with the shot, it shortened, but it shortened slowly. You're trying to make it fast, but it has to be slow because the shot has a lot of opposition for you. So the shot is moving slowly, so your muscle is shortening slowly. With the apple, you again try to shorten as quickly as possible, and the muscle is active, and it shortens, and it shortens very fast, but it cannot make as much force. So in both of these situations, the muscle gets activated, muscle tries to shorten, and it succeeds in shortening. So the muscle tried to shorten, and it actually shortened. And these are called concentric muscle conditions. And it's called concentric, meaning common center. It means simply that both ends of the muscle are moving towards the middle of the muscle. In other words, the muscle is shortening. So with the apple, what we have is fast concentric conditions. And in fast concentric conditions, the muscle cannot make a lot of force. With the shot, we have slower concentric. You're making a full effort both times, okay? But it's a slower concentric conditions here with a shot, and you can make a large force that way. Okay, so let's see now a different situation in which instead of having a shot or an apple in your hand, you have a brick wall. Your hand is pushing against the brick wall. So you activate your muscle, you try to shorten the muscle, and your hand tries to move forward, but it cannot move because there's a brick wall, so you cannot move it. So these are called isometric muscle conditions. Equal length, the muscle is activated, but it cannot shorten. It tries, but it cannot shorten. Okay, well, in isometric conditions, a muscle can make larger forces than in slow concentric. All right, so now let's see a fourth situation here. Let's say that you're trying to extend at the elbow, and you're trying to shorten your triceps, extend at the elbow, but something is opposing you. So you have an elephant pushing in the opposite direction. And so you're trying to move your hand forward and up, but because the elephant is pushing in the other direction, you're forced to flex at the elbow. You're trying to extend, but you're forced to flex at the elbow. This is called eccentric muscle conditions. The muscle is activated, it is trying to shorten, but it is forced to lengthen. And of course, the terminology eccentric means away from the center. So it just means that the two endpoints of the muscle are moving away from the center of the muscle, means the muscle is lengthening. That's all it means. So the muscle is active, trying to shorten, but it is forced to lengthen. Well, in eccentric muscle conditions, the force that you can make with a muscle is bigger than with isometric. Okay, so this is a situation where the elephant is being nice to you. The elephant is pushing backward, not too hard. So your hand is moving backward, not very fast. But the elephant could get angry, and then, oh, wait a minute, this is not advancing. Yeah. The elephant could just push a lot harder very quickly. So you're trying to shorten the muscle, but is forced to lengthen very quickly. This is called fast eccentric conditions. And in fast eccentric conditions, the force you can make is still bigger than in slow eccentric conditions. Okay, so let's summarize this. This is a graphic. In this graphic, we have in the horizontal direction is the speed of the muscle. Well, the muscle is shortening in this direction. Here, the muscle is lengthening. So we have concentric conditions on the right, have eccentric conditions on the left. And in the vertical direction is the maximum muscle tension that you can make at each speed. So if you look, for example, at the apple, this will be what happens around here. The force you can make is small. If you have the shot, the force you can make is bigger. If you have the brick wall, the force you can make, well, we can't see it, but it's bigger still. With the elephant making you move backward slowly, the force that you can make is still bigger. And when the elephant is making you go backward very fast, then the force you can make is still bigger. Okay, so this is a very important concept that applies to everything in track and field, everything in athletics, and is a very important muscle mechanics concept to have. I'm wondering here, would it be good to see if people have any questions at this point, or maybe just continue? I don't know. What do you think?
I think that right now we don't have question in the chat. I don't know if the guys are pretty shy or if they have understand everything. I would assume the second. So yeah, maybe I think that we can go ahead. Maybe double check. Stefano, credi che ci siano domande o possiamo andare avanti?
No question.
Okay, so we can go.
Okay. All right. So now that we know something about muscle mechanics, there's a force-velocity relationship there. Now we're going to be looking at a standing vertical jump. So we're not going into high jump yet. We're looking at a standing vertical jump. This is a jump in which the athlete starts simply standing up. The athlete flexes the legs, and then the athlete extends the legs again. And at the end of this, the athlete has a big upward vertical velocity. So initially, the center of mass is here. It has 0 vertical velocity. Then the athlete relaxes the leg muscles, and gravity pulls the athlete downward. So velocity goes from 0 to maybe -1, -2 meters per second. So when the center of mass is about maybe here, maybe you have a downward velocity of maybe -2 meters per second. Then the athlete activates the leg muscles again, trying to extend the leg. Of course, the legs are flexing because gravity has been pulling you down, but the muscles get activated, and the muscles are used to slow down this downward motion. And finally, when you reach this level here, vertical velocity is back to 0. So you go from 0 to -1 meter per second, -2 meters per second, and then -1 meter per second and 0. So at the bottom point here, your vertical velocity is 0 again. So as you are slowing down this downward motion, so between this time here and this time here, the muscles of your legs will be in eccentric conditions, right? These are these very strong conditions. You're very good at stopping this downward motion. So here we are at the low point. I'm going to go to the right graph here. At the low point, your velocity is 0. And you're going to be changing that from 0 to here. You want velocity to be the biggest possible that you can. So you want to go from 0 velocity to 20 meters per second of vertical velocity if you can. The bigger the vertical velocity, the better. So you want to change from 0 to a big upward vertical velocity. Now, during this whole period between here And here, your muscles are trying to contract, they're trying to shorten, they succeed in shortening. And initially, at the very bottom of the jump, you're in isometric conditions, but then as you begin moving upward, they go into slow concentric, fast concentric conditions. So all of the generation of upward vertical velocity is happening in concentric conditions. So we used before eccentric muscle conditions to slow down the downward motion, but then at the end of that, you have zero vertical velocity, you're at the bottom. So all the generation of upward velocity is happening in concentric conditions, which are these weak muscle conditions. Now, what we would like is to have our muscles be in eccentric conditions while you're generating upward velocity, because those are the conditions in which you can get the biggest possible force. But of course, this seems impossible, right? If you're moving upward, your muscles will be shortening, and therefore they have to be in concentric. How can you be in eccentric conditions, not while slowing down motion that is the downward motion, but while you're speeding up motion that is upward already? We would like that, but it seems impossible. Okay, well, it is impossible to use eccentric muscle conditions to increase upward velocity in a vertical jump, in a standing vertical jump. However, we're going to see that in a high jump, you can use eccentric conditions not only to slow down downward movement, but to actually produce upward movement. And as Americans would say, you can have your cake and you can eat it too. Okay, so here's a high jump takeoff now. Finally, we get back to high jump. Okay, so
yeah, finalmente si torna al salto in alto e vediamo il takeoff.
So this is a typical high jump takeoff. And you see the standard pattern of what happens in the takeoff leg. So initially, you put the leg on the ground and the leg is close to straight. Then the leg flexes. And then the leg extends again, okay? So at the end of the run-up, you plant your foot clearly ahead of your hips. And this is a very peculiar thing for a high jump. You have a fast run-up, you plant your foot in front of your body, and then your leg flexes, and then your leg extends again. Okay, here we see the start of the takeoff phase, and that green curve, that is the path of your center of mass in the last step of the run-up. And you can see that this path is pointing a little bit downward over here. This is because it's composed of maybe 7 or 8 meters per second in the horizontal direction and maybe 0.3 meters per second minus 0.3 in the vertical direction. So it's almost perfectly horizontal. It just has a little bit of a downward motion to it, but you can think of it as being moving essentially horizontally at the start of the takeoff phase. Okay, so this is the critical part of all of this. During the first half of the takeoff phase, we have that the takeoff leg flexes at the knee. So you're here, you have essentially a straight takeoff leg there. The knee is 180 degrees, so pretty much straight. And then you go from that configuration to maximum flexion here. So between these two figures, the knee is flexing and your muscles will be in eccentric conditions. Now I have to make a little aside here again. The muscles that you're using during the takeoff phase are going to be primarily, it's going to be the quadriceps and the gluteus. Okay, and it'll be useful for us just for simplicity to think about the quadriceps alone, but the gluteus is also involved. Okay, but let's think quadriceps. Okay, now look at the center of mass. The center of mass initially was moving pretty much horizontally. It had a little bit of downward vertical velocity, But during this first half of the takeoff phase, the center of mass is going upward almost all the time. Okay, at this point here, maybe it had a downward velocity of minus 0.3 or 4 meters per second, but that goes to zero almost immediately. In the first 0.02 seconds, that goes to zero. And then from that point onward, maybe around here, from there, it's all in upward motion. So your center of mass is going up while the muscle is in eccentric conditions. So we're using these very good conditions, for muscle force. We're using them we are using them to slow down the downward motion for 0.02 seconds. But then after that, all of this first half of the takeoff phase, we're using eccentric conditions to generate upward vertical velocity. It's the paradox of the first half of the takeoff phase. Now, the second half of the takeoff phase is less interesting. This is a time when the leg goes from being maximally flexed to going back to pretty much totally extended again. So the muscle is in concentric conditions, and the center of mass is going up. Okay, yeah, that's good, but you are again in the weaker conditions. This is not the interesting part. This is similar to what is happening in the standing vertical jump. Yeah, the muscle is shortening and you're moving upward, concentric. Yeah, the interesting part was the first half where the muscle is lengthening and you're going up already too. Approximately 1/2 of the vertical velocity that you will have at the end of the takeoff, about 1/2 of that is produced while the muscles are in eccentric conditions. And they're produced in the first half of the takeoff phase when the muscles are in eccentric. Okay, so by using this way of doing the takeoff, you are maximizing the size of the force that the ground makes on you, because you're making your muscles be in eccentric conditions part of the time, so you can get really big force. The problem is that in the standing vertical jump, the force you got from the ground was vertical. It was all good, useful force. But here, the force you get from the ground points upward and backward, right? So it has two components. It has a horizontal and a vertical. And this horizontal component is useless. That doesn't help you to do anything. It has to be there because it's part of the whole mechanism, but it's not the useful part. This, the vertical component, that is the useful part. So ideally, we would like to have a force of this size, right? This whole diagonal force. You would like that force to be in the vertical direction. You would like it to be like this, all pointing vertically. This is what you would like, but that is impossible, of course. You have only this amount of force, just up to here. So you lose a little bit, you waste a little bit of this force because it doesn't point perfectly vertical, but you can see that the difference in size between the two forces is not very large. So by using this mechanism, of using eccentric and then concentric, you get a really big force, and it's so big that even though you cannot use, not all of it is useful to you, it's still a net advantage for you. Okay, so from a practical standpoint, what does that mean for a high jumper? It means that it's good to have a fast run-up, because if you have a fast run-up, it means that your leg muscles are going to be in faster eccentric conditions, and in faster eccentric conditions, you can your muscles are able to make bigger forces. So the bigger the run-up speed, the more eccentric your muscle conditions, and therefore the bigger the force you can get from the ground. Okay, so we know that by using eccentric conditions, this is a very important thing for the high jump technique. But there are other factors that come into play here also. They're not as important, but they also play a role. And some people think that those other factors may be the important ones. Okay, so if you look now here, one possibility is a stretch reflex mechanism, which is a good thing. So when you come in fast in your run up, you plant your foot on the ground and your quadriceps muscle is stretched. When it gets stretched, any muscle, when it gets stretched very suddenly, it sends a message to your spine. And then the spine sends, and the message says, hey, I'm getting stretched here. What should I do? And the message that comes back from the spine says, oh, you're getting stretched. Well, look, activate really strongly. So it takes a little bit of time for this stretch reflex to happen because you get the muscle gets stretched, then the message goes through the nervous system to the spine, and then another message comes from the spine back to the muscle. That takes time. So by the time that the message arrives at the muscle and increases the force the muscle can make, you may not be in eccentric conditions anymore. Maybe you're in isometric, or maybe you are in the concentric stage of the jump. But in whichever point of the takeoff phase, this stretch reflex comes back, it may help you to make a slightly bigger force. So yeah, this is another reason why you want a fast run-up. The faster the run-up, the faster the stretching of the muscle, and the bigger the stretch reflex. Right, another factor that comes into play is what I call leverage. Leverage is a bad thing. It has a negative effect. When you activate a muscle, let's say the quadriceps, if you activate the quadriceps, that makes your leg try to extend and makes your foot press against the ground harder, okay? Now, if the leg is almost straight, then the force the foot can make on the ground is very big. But if the leg is very flexed, you have what is called bad leverage. And that means that for a given force the muscle makes, the foot can make a force that is smaller. So with good leverage, for a given muscle force, you make a big force on the ground. With bad leverage, with the same amount of muscle force, the force you can make on the ground becomes smaller. So let's see an example of this. Let's say that you are doing a squat with weights, and you put a big weight on your back, maybe 200 kilos on your back, okay? Well, maybe the barbell weighs 200 kilos. Maybe your body weighs 70 kilos, okay? And if you don't flex your legs very much, you can do it, you know? Probably this will be too much, but if you don't have much flexion in your knees, you can handle that, which means that the foot on the ground is making a force of 270 kilos. Okay, so that way your weight, you plus the barbell, is 270 kilos downward. You make a force of 270 kilos downward on the ground with your feet, and the ground makes an upward force on you of 270 kilos. Okay. Now, if you flex your legs more, and you have the same 200 kilos on your back, then you find that now here you have good leverage on the left, here you have bad leverage. The knees are very flexed. And you will know that if you have 200 kilos on your back, if you flex a little bit too far, you find that you cannot hold that position. You'll just collapse. The whole thing will go down because you have bad leverage. So even though your muscle, your quadriceps, is making the same force as before, the quadriceps is making the same force as before, but the force you can make down on the ground, it becomes smaller. Maybe it's 160 kilos, maybe. And you have now 270 downward. Okay, by weight, and you have 160 upward. the total force is negative, it's downward, so you're going to collapse. Well, this is an experience that all of us have had, right? If you put weights on your back and you bend your knees just a little bit, no problem. But if you bend your knees too much, then you cannot handle this weight anymore, and everything would collapse. You have to let go of the weights, or it's going to crush you below them. And this is because when your knees are very flexed, you have bad leverage. So in a high jump, always you will come in the run up, plant your foot ahead of your body, the leg, the knee will flex a certain amount, then it will extend again. But if you come in, so it's unavoidable. You go from very good leverage to worse leverage, and then back to good leverage in the second half of the takeoff phase. It is unavoidable that you have to go through some positions which have bad leverage. So before I said the faster the run up, the better, but there's a limit to this, because if your run up is too fast, then when you plant the leg on the ground, the knee is going to flex too much, and your leverage is going to become so bad that overall the force you can make on the ground becomes very small all of a sudden. So if that happens, then maybe you will not be able to extend the leg at all. You just go directly into the pit. You will not take off, really. You just go directly into the pit. Or maybe, yes, you can still extend the leg, but in a weak way, and it'll be a very bad jump. So you want to have a fast run-up, but up to a certain point. If you go too fast, that can be a problem too. Okay, so if you're a very strong athlete, if you have a killer takeoff leg, you can come in really fast and no problem. You can limit the amount of flexion and everything will work great. But if you're a weaker athlete, then you cannot come so fast. You have to come in more slowly, because if you come in too fast, then you'll have bad leverage and it'll be, your leg will collapse. You will have a very bad jump. Okay, so this is how you get a big force. By using a fast run up, you can produce a big force on the ground. Remember, there are two ingredients for producing a big upward vertical velocity at the end of the takeoff phase. One of them was you needed to receive a big vertical force from the ground, big upward force. The other one was that you needed a long time, a relatively long time. So how can I make my time be long? Well, one way is not to really use my muscles too much. You know, you put the leg in there like a wet rag, and you put your leg on the ground and let it flex. Then you don't make a big effort. It takes forever to get it off the ground. That's one way to have a long time. That's not what you want. If you are making the biggest possible force on the ground, then the only way to have a long time for that push is by maximizing the vertical range of motion of your center of mass from the instant of takeoff to the, from the start of the takeoff phase to the end of the takeoff phase. Is this delta Z distance here. So you want to be low at the start of the takeoff phase, and you want to be high at the end of the takeoff phase. That distance should be maximized. So you want to be low at the start of the takeoff phase, and you want to be high at the end of the takeoff phase. How can you be high at the end of the takeoff phase? Well, you have this leg is high, so that makes your center of mass be high. Your plantar flexed here, so that also makes the center of mass be higher. Your arms are in a high position, so that also tends to increase the height of your center of mass. So lead leg up, plantar flex, the support foot, the support ankle, the arms are high, and also your body, you want it to be as close as possible to vertical. All this is not very difficult to do. I can do it very well, okay? This is not the great, wonderful thing. Anybody can achieve a high position at the end of the takeoff. What is difficult is achieving a low position at the beginning of the takeoff phase. And that's difficult because to be low here, so we're talking about this point here, you want to be low, but if you want to be low here, you already have to be low here in the final steps of the run-up. And it's very difficult to do that. it's difficult to, I'm telling you, you have to run fast. And we see that you're going to have to do many other things. You have to run fast. You have to prepare your arms for the takeoff. You have to do a lot of things in the final steps of the run up. And now I say, oh, and do that while your hips are very, very low. That's very difficult to do. And it requires a lot of training. You really have to work on this in your training. All right, so as a result of this difficulty, many high jumpers do not know how to run fast and low. That combination is difficult to do. So let's look at this graphic here. And the horizontal, each one of these dots is one jump by a different athlete. They're all from an American national championship. I can't remember which one it was. These are all men here. And I have in the horizontal is the final speed of the run-up that they had. And in the vertical direction is the height of the center of mass at the end of the run-up. Of course, if you have a tall high jumper, that high jumper will tend to be high at the end of the run-up because they're just tall. So to be able to compare people properly, we take that height in meters and you divide that by the standing height of the athlete. So that's why these values here are percent values. It's percent of standing height. So the athletes that are on the right part of the graph, they have a fast run-up, and the athletes on the left have a slow run-up. So the athletes on the top of the graph are high at the end of the run-up, and the ones at the bottom are low at the end of the run-up. So let's see what we would expect to happen if we take this athlete, and if we move his dot to a different position on this graphic, what would happen to his results? Okay, so what if he moves to this upper left quadrant here? That means slower run-up. That's bad. It means higher position at the end of the run-up, which means less range of motion for the takeoff phase, and therefore less time to get force from the ground. So everything in this direction is pretty bad. What if you moved into these two quadrants? Well, here we have a mixed bag. You have good things and bad things. If you move into this quadrant, you're faster, that's good, but you're also higher. So smaller vertical range of motion available in the takeoff, so that's bad. So if you move the dot in this direction, okay, if you move the dot in the original direction, you would expect this athlete to reach less height in the jump. If you move into this quadrant, you may jump a little bit better, you may jump a little bit worse because you're combining some good thing and a bad thing. If you go in this direction, is the same thing. Here, you'll be going slower, which is bad, but you'd be going lower, which is good. So it's a combination of good and bad things again. So changes in this direction, this diagonal direction, it may make you jump a little bit higher, a little bit lower. There's not too much change. Right, so now if you move into this quadrant, what do you get? Well, it's a faster run-up, that's good. You're lower at the end of the run-up, it gives you more time to receive force from the ground. Everything is good here. If you go in this direction, you expect to improve your height of the jump. Okay, well, yeah, you expect an improvement unless, let's say that you're near the buckling point. Remember, if you go too fast and too low, you will reach a position of very bad leverage and you will jump less. So if this athlete here, if he is very near the buckling point and you make him go any faster and any lower, maybe he'll buckle and you'll have a bad result. All right, so we have a problem here, right? How can we figure out if it's good to change the point to go farther to the right and farther down? Okay, so this is initially, I followed a certain logic to figure this out, and it's going to turn out that there was a problem with the logic. The first thing I said was, I thought, okay, look, all of these are finalists in the National American Championship. They're all jumping, probably, I can't remember, but somewhere between 220 and 230. So some of them obviously will have stronger legs than the other ones, but they probably are not too different from each other. So let's assume that these 10 athletes there They're not twins, they're not triplets, they're, I don't know, tentuplets. They're all the same. Let's imagine that they're all the same, really, in their qualities. Their genetics are the same, their training is the same. They all are the same type of athlete, exactly. Let's imagine that. And then we'll follow the logic. So, by the way, these jumps, they're all, these 10 jumps you see there, they're the best jump of the competition for all of these 10 athletes. So if we look at these two guys, we would say, okay, look, you're very fast, you're very low. Maybe you could go faster and lower, but right now, and we're very conservative. When we tell people to make changes, we don't say, try this crazy thing, maybe it'll work. No, if we tell them try this, it's because we think it's going to work. So we're very conservative. So in these two guys, we would say, you're okay. Now, looking at these two guys here, would say, you're pretty fast. Your speed is very good. You're very far to the right on the graph. You're very high, but I don't know, maybe you're going so fast that overall you may be near your limit for buckling. I don't know. Maybe you can be a little bit lower, maybe. But if you stay this way, I'll say you're okay. I'm not going to complain. Then this guy here, well, he's very slow, obviously, but he's very low, extremely low. And we'll say, I don't know, maybe you're close to buckling too. Maybe not. Maybe you should come in a little bit faster, maybe. But if you stay where you are, next year I will not complain that you did the wrong thing. I'll be okay with that. Then we get to these two guys here. They're slow, they're on the left, they're high, they're on the top of the graph. Oh no, these guys have a problem. These guys have to move in this direction. Okay, well, all that logic would be very nice if these people were really tentuplets. Is there a word like that? Tentuplets? But they're not twins. First thing is, obviously, some of them are jumping 230. Some of them are jumping 220. That is some difference. It's not a huge difference, but it means that they're a little bit different from each other. And another factor, more important one still, is that some of these athletes are very tall and some of these athletes are short. They're not really short. Nobody is short in the high jump meet. You know, what we call the short high jumpers, if you see them on the street, they're all taller than average, but they're short compared with other high jumpers. So the tall guys start their airborne path from a higher position. So this is at the end of the takeoff, right? When they're leaving the ground, they're very high, and therefore they have to travel very little to reach the bar. Whereas the short high jumpers, they start at the end of the takeoff phase. When they leave the ground, they're in a much lower position. So they have to travel a long distance upward. So to achieve that, they must have a much stronger takeoff leg than the tall guys. So these athletes, they're not tentuplets. Now, these guys here, remember we said, oh, you're okay, you're fine, you're very fast, you're very low, great. But maybe not. Maybe these guys are one of these short people who have an explosive, they have a Superman takeoff leg, and they are not at their optimum. Maybe these guys should go here. In the same way, these two guys here, who are very slow and very high, and we told them you definitely have to go faster and lower. Maybe they're one of these very tall guys, and maybe they're the one who jumps 220 instead of 230. So maybe these two guys are very, relatively speaking, because this is the national championship, but maybe relatively speaking, they're two of the weakest people in here. And maybe if they go any faster, then it's not going to work. The leg is going to buckle. So it's going to explode. So the logic that I used for my first report from the first year I did this, it was not good because there was a bad assumption. Okay, so obviously we need some measure of power of the takeoff leg. And power here, power in mechanics and physics is force force multiplied by velocity. That's not what I'm talking about. This is like power in the sense that it's used by a coach, you know. Oh yeah, he has a killer takeoff leg. Great, lots of power. This is how I'm talking here now, okay? Okay, so we need to measure somehow. So how could we do it? Well, the first thing that comes to mind is we have them do a squat. Okay, squat lift. Okay, well, that's not going to work very well. And the reason is this. When you do a high jump, the muscles, your quadriceps goes from fast eccentric to slow eccentric to isometric momentarily to slow concentric to fast concentric. So the muscle goes through the whole range of speeds of eccentric and concentric in a high jump. But in the squat, it's different. In the squat, the whole movement is very slow, right? You put these big weights on your back, you go downward slowly, reach the low point, then go upward again. So your muscles are in slow eccentric as you go down, momentarily isometric at the bottom, and then slow concentric as you go up. So a squat is a very good measure of how strong your muscles are in slow concentric, in slow eccentric, isometric, and slow concentric. But it tells you nothing about how strong you are in fast eccentric or in fast concentric. Okay, so that's not good.
No,
What else can we do? How about a standing vertical jump, the one we saw before? Well, in a standing vertical jump, you start in the high position, you relax your muscles, then you let yourself drop and you use eccentric effort to slow down that downward velocity. But then all of the vertical velocity, which is what is going to determine what is the quality of your vertical jump, all that vertical velocity, it's all in concentric. So that does not tell you anything about how good you are in eccentric conditions. Well, not a good measure either. Okay, so that's the problem. We need some way of measuring the power of the takeoff leg. And I came up with a measure that is not perfect. It's definitely not perfect. I will explain it. But it's the best one that I could think of. Let's see what it is. We use the vertical velocity that the athlete gets at the end of the takeoff phase. We use that as a measure of your power of your takeoff leg. Why is this not a good measure? Well, it's because the vertical velocity, it's not a perfect measure. It's a good measure, but it's got a problem. The vertical velocity that you can achieve at the end of the takeoff phase, it depends on your body a lot. It depends on your genetics. You know, as they say, you have to choose your parents very carefully to be a high jumper. So it depends on your genetics, depends on your training, what body you have, which is what we're trying to find out. But it also depends on technique. So you can have two people that have the same body, but one of them comes in at 8 meters per second and gets a lot of vertical velocity. And the other one, who does not know how to high jump, comes in at 5 meters per second and produces a smaller vertical velocity. So you have two people here with the same power in the takeoff leg, but one of them gets a bigger vertical velocity and the other one has a smaller vertical velocity because technique is a factor that affects this vertical velocity at the end of the takeoff phase. Okay, so why do I say that this is a good, not perfect, but good measure of power? It's that of these two factors, two global factors that are your genetics and your training, how good your body is, and technique, which of those two factors is the one that affects most the vertical velocity? Your body, the quality of your body is the most important of these two factors. Because, and of course, we can't, I'm not going to say that technique does not matter. It does matter. It is a factor, but it is smaller than the body of the athlete. So for example, let's say we take me. Let's say I'm one of these jumpers, right? And I'd be at the bottom end of the bad guys there, right? So let's say that for me, I'm using, I'm producing a vertical velocity of 3.2 meters per second at the end of the takeoff. Okay, let's say I produce 3.2, but my technique is not perfect. So maybe I can do 3.3, 3.4 if I just refine everything, if I come in a little bit faster, a little bit lower, and I do other things very well. Maybe it could be at 3.4. Could I be at 4.6? No. So if you offered me, okay, look, you're going to try to be in the Olympics, what would you like to have from Sotomayor? Would you like to have his body or his technique? I'll take the body, because if I could have Sotomayor's body, then my technique would not be as good as his technique, but I can come up with something reasonable so that, yes, I'm not going to jump 245, but I'm certainly going to jump 230, 235. But with my present body, I need Virgin Mary to come down from heaven for me to jump 2 meters, right? So the main factor is the body. The technique, it is a factor, but it's a smaller factor. So when I try to evaluate my quote unquote power, if I look at my vertical velocity, and let's say that it's 3.2 right now, but really if I had a better technique, it could be 3.3 or 3.4 with the same body. Well, that's okay. 3.2, 3.3, 3.4, they're very similar numbers. So I have a fairly good estimate of how strong I am. If you look at Sotomayor, he'll have like 4.7. And if his technique could be improved, maybe he could be at 4.8. Or if it got a little bit worse, it could be 4.6. But he's going to be at 4.6, 4.7, 4.8. So with any of those numbers, they're going to tell me, look, Sotomayor is a lot stronger than Da Pena. So we have now a measure, an imperfect measure of the power of the takeoff length. So let's start using that to try to figure out what is the optimum for every athlete. Okay, so I'm going to be making a graph that is going to be showing, in one part of the graph is going to show vertical velocity at the end of the takeoff phase. So that means if it's a big number, it means it's a powerful athlete. If it's a small number, it's a weaker athlete. Okay, and then we're going to plot that against the final speed of the run-up. Okay, so here's the graph. Okay, so in the horizontal part of the graph here, we have vertical velocity at the end of the takeoff phase. So Sotomayor would be on the right. Okay, and Da Pena would be on the left. Okay. Then on the vertical part of the graph, we have the final speed of the run-up. So each one of these jumps, each one of these dots is one jump by a different high jumper. So powerful athletes are on the right, good athletes, the elite athletes are on the right, and Da Pena is on the left end. Okay, and now in the vertical is what speed did they use in their run-up? So we find that there's a scatter, but there's an upward trend, clearly, so that the stronger athletes, they use faster run-ups. Why is that? Well, by trial and error, the weaker athletes, if they have tried coming in at 8 meters per second, they put the leg on the ground and buckled and said, well, this is crazy. So they use slower run-ups. Whereas the better athletes, they find that they try faster and faster run-ups, they can jump higher and higher and higher. So they normally use a higher speed than the weaker athletes. So let's think a little bit about this run-up speed. It's difficult to do a fast run-up. You have to concentrate. You really have to put a lot into it. It's very easy to do a slow run-up. So in this competition, let's say that you have one athlete, and let's say that we have a crystal ball, and the crystal ball says that the optimum speed of the run-up for this individual is, for example, 7 meters per second. Magic, somehow we know it's 7. And this athlete in a competition first uses a run-up of 5 meters per second, very slow, 5 meters per second. And, he jumps a certain height. But somebody told him, if you go faster, you probably will jump higher. So he tries 6 meters per second. So he tries it and boom, he jumps a little bit higher. Oh, great. Okay, I'm not jumping at 5 anymore. I'm always jumping at 6. So then somebody says, well, but maybe you can go still faster. So he comes in at 7. Wow, still better performance. Okay, I'm coming in at least at 7 from now on. This is very good. So then somebody says, oh, try even faster. So he comes in at 7.3. Comes in at 7.3. Remember, the optimum for this guy was 7. He does not know that, but we have the crystal ball that 7 is it. So he comes at 7.3, plants the leg on the ground, the leg buckles, he goes straight into the pit. It's a disaster. Now, this athlete has, to run at 7.3, that takes a lot of effort. You really have to think about it, and it's hard to do. And when you do it, your leg buckles. What do you think he's going to do in his next jump? So he's going to go back to 7 meters per second. That worked great. And it's easier to do. It's easier to run at 7 than at 7.3, and you get better results. Problem solved. He said he's going to be jumping at his optimum, okay? Now, maybe there's some athlete that is crazy, and he goes at 7.3, and the leg buckles, and he just keeps coming at 7.3, 7.2, 7.4, 7.3, and disaster. I don't think anybody would do that, but some people may do that because they may, it's not necessarily that your leg totally buckles. It could be that it flexes too much and then you don't get as much height, but you think you're doing well. So maybe some crazy athlete is coming a little bit faster than optimum. Okay, so this guy ends up at optimum. At 7, which is his optimum. Now let's say somebody else, another jumper, again, a crystal ball says his optimum is also 7. But this person starts at 5 and he gets certain height, then he goes to 6, he goes better, okay? And then somebody tells him, okay, go to 7, and this guy cannot do 7. Why not? I mean, 7 is not very fast. Anybody can run at 7 meters per second, but you have to run at 7 and get low and prepare your arms and have your curve and boom, there's a lot of things to do. And this guy does not know how to run at 7. The best he can do is come in maybe at 6.5. And that's the best he can do. So he comes all the time at 6.5 when his optimum is really 7. So if you look at all athletes, you're going to find that some of them are going to be at optimum. Very few are going to be faster than optimum, and quite a few are going to be slower than optimum. Wait, I don't know if I said that right. Some are going to be at optimum, very few faster than optimum, but quite a few, a good amount, also are going to be slower than optimum. So when you look at the average of all of these athletes, on average, they're going to be going slower than optimum. Okay, so if you look at our graphic here, this is the mean. This is the regression line. This is the mean. Okay, so the athletes who have a run-up speed, the athletes who have a takeoff leg that produces 4.4 meters per second of vertical velocity, this is the average speed in which they come. For the athletes who are weaker, they can only produce 3.4 meters per second of vertical velocity. This is the average speed at which they come. And average is worse than optimum. Average speed is slower than optimum. So, important conclusion. If your point is on the line, on the regression line, you are too slow. If your point is below that line, so the point is somewhere around here, you're even slower. And if you're here, you're terrible. You're super slow. You're slower than optimum, much slower than optimum. where is the optimum? It's got to be above the regression line. It's got to be above this. Where above? Well, we don't know exactly, but it's going to be pretty high, because how many people, what percentage of these high jumpers do you think are systematically coming in too fast? Very few. They're these crazy kamikazes that they just don't happen, because you can correct that easily. So the optimum is probably somewhere around, I don't know, let's say this is a kamikaze here, and maybe this is another one here. So maybe the optimum is around here. So when I'm going to give advice to athletes, I use a conservative, again, a conservative estimate. So I say, if you are less, okay, the optimum, I say the optimum is 1 standard deviation above the average. So this is, it means that about 2/3 of the points in there, up there, 2/3 of the points are below optimum, and 1/3, that's a lot of people. I'm sure there's not that many, but 1/3 is beyond the optimum. It's kamikaze. So maybe somewhere like this is where I put my optimum. Okay, so the optimum is probably higher than that, but I use it in here. And this is what I use for my optimum. The 1 standard deviation comprises about 2/3 of the athletes, which assumes that 1/3 are coming faster than optimum, which there's going to be less than that. So I'm being conservative. And that's it.
So, Professor, thank you very much.
Thank you. It's my
With
pleasure.
us. It has been a very, very high pleasure for us. So see you next time.
Okay.
We get in contact to set the next date, probably after the summer.
Yeah.
And thank you again. You are a very, very, important person for us. So may I ask all you, friend? It could be very important for us.
Okay.
Grazie.
Thank you very much.
Thank you.
Thank you.